So, welcome students. So, welcome to today's class. So, we are in the class MA425 Topology. Okay, and this is lecture number 4. Lecture number 4. Okay. So now recall that we have discussed about the basis of the topology and sub-basis, right? Now we would like to discuss to formulate new topologies from existing topology. Okay, one of such topology is called the product of topologies. Okay, a product topology, we will write down that. Okay, so this is the sections. The product of topologies. Okay, so we will start these sections by 2 first, and then we will go for the generalized result. Okay, so what is the setup? So let we have two topological space. So let x and tau x and say y tau y be two topological space. Okay, and obviously the natural way to define a new set from these two sets is so maybe we can write down z, which is x cross y, the Cartesian product of x and y, right? So what does that mean? That means the elements of these are of this form, right? It's x comma y. This element of this, right? Whatever, yeah. So x belongs to x and y, small y, belongs to capital Y, the set. Okay. So the natural way one can ask that if you know that x and y have topologies, can I define a topology on x cross y which are kind of coming from the existing topology? And the answer is yes. And this topology is called the product topology. So product topology on x cross y. Okay, what is this? So here we will define the basis element, and then obviously if you know the basis element, then take any union of those elements that will forms the topology, right? So what is the basis element here? So the basis element on these you can write down of this form, say okay, so this is obviously, so let me define it first. So I will take this is of all those collections, say u cross v belongs to this is subset of x cross y, such that u belongs to that tau x and v belongs to tau y. Okay, so I'm collecting all those sets of these forms. Okay, x u cross v, such that the first component u's are actually open sets in x, and second component v is open set in y. Okay, and then you can check that this forms a basis. This forms a basis, okay, of some topology, which is called the product topology, which we called product topology on x comma, right? Product topology on x cross y. Okay, So the natural question is that how do you know this forms a basis? So and obviously you can easily check it that this forms a basis. So see, there are two ways to check something is a basis. One is obviously the definition, and then we prove another equivalent condition. And by definition, you can check first of all it has to cover the full thing, right? So that this is condition one, and that B covers x cross y. Right? This is trivial because I mean x y itself is right as this set x y itself belongs to this collection, right? Okay, so this is first condition. And second condition, what was the second condition? Second condition was that given any things intersections also contains one, right? And that is also trivial because if you have two elements, so for example u1 cross v1 and u2 cross v2, suppose this is two elements inside B, then obviously you check that intersection of these two. Okay, yeah. u1 cross v1, what is the intersection of these two things? u2 cross v2. Okay, can anyone tell me? So this is nothing but exactly u1 intersection u2 and then cross v1 intersection v2, right? Now note that both u1 and u2 are open set in tau x, so the intersection is also open. So this is something u3 and this is something v3, right? Obviously, so this is belongs to tau of x and this portion belongs to tau of y, right? By definition. So u3 and uv3 both are open and hence this is belongs to B. So intersections are also inside these, and hence if you choose any elements in its intersection of two elements, then there exists an element which contains intersection, and that is nothing but the same element, right? v3 equals v4. So how do you think pictorially? So let me just draw a picture so that you can understand better. Suppose this is okay, yeah. So try to, yeah. So suppose in my so I have open sets in U. So this is x-axis. Maybe you can think this is y set. Okay. So this x space we have like U. For example, you choose an u1, this, okay, and on u2 say this, okay, because you have intersection here. Can you see that? Okay, and similarly you choose, for example, this is your v1 and this is your v2. Okay, now corresponding to this, what you have? So you have right, so this corresponds to this. So this so interior means the inside other than boundary interior of this. So this portion is nothing but u1 cross v1, right? u1 cross v1 is this portion. Similarly, for u2 for this. So this is this portion, the interior of this portion, and one is interior of this portion, right? So this is interior of this portion is u2 cross v2, right? Okay, and what is this intersection? So this intersection portion is nothing but, you check, this is nothing but this cross this, right? So what is this? First you are taking intersection here, u1 u2, so this is u1 intersection u2, sorry, and then this one is v1 intersection v2, right? So this one is nothing but u1 intersection u2 cross v1 intersection v2, right? So exactly the same thing which I wrote here, I am just showing you by pictures. Okay, so that means it forms the, it satisfies the property of basis. So So obviously this, if you take the collections of Cartesian product of sets which are individually open in that each topology, they forms a basis. And now if you know how to find out the topology out of the basis, now you take all kind of unions of those elements, that will form the topology on X cross Y, which we will call the product topology. Okay. Now question is that whether I mean, this is a basis element, right? So do you have a smaller collection which also forms a basis? Like this is a big collection, right? So you have open sets of all open sets of X, all open sets of Y, and you are taking the Cartesian product, right? The answer is yes, we have a smaller collection that also forms a basis. And what is that? So this is, we can write down by a theorem, and that will tells you that if you take only the Cartesian product of basis element of each topology, that will give you a basis element of the new topology. So so let me write down properly. So for example, so I have this, this is given to me X tau and Y tau Y, right? Now let me write down my basis, say Bx is the basis for the topology tau X, and By is the basis for topology tau Y. Okay, and now I am going to define another element, another set, say capital B, which is of this form, collection of all say for example all of the form B1 plus B2, such that B1 inside Bx and B2 inside By, and this also forms a basis. Okay, and not only that, they generate the same topology from which is a product topology. Okay, so now check that this forms a basis. Okay, first of all, how to check this forms a basis? And this is obvious because to check, see, there are two ways to prove basis. One I already said, and pure example. There is another way, right? What is that thing? So you take an open set, an element in the open set, and check that you find out an element of the basis which also contain the point, and it is inside the open sets, right? It was discussed in I think in the second lectures. Okay, so you use that formula to prove something is a basis. Okay, so to check this B forms this forms a basis. So let us you start with the open sets, any open sets, and then you check that you have a basis element inside that. Let us open sets W. So this is open sets, means open set in the product topology. Okay, open sets in the product topology, that tau X cross tau Y. Okay, and now we will check that it is actually and obviously a point of, if you choose a point and you choose some point, say X comma Y, which is element of W. Okay, so then you need to find out that thing, right? Now because this is open set in the product topology, so as W is open in the product topology, there exists U, which is element of this, and V, which is element of this, such that what happened, such that your the basic open sets U cross V, this actually inside W, and your points xy is an element of this, right? This is by definition of topology. The topology is already defined. Okay. Now what we want to check? We want to check that W also contains one element of this new basis. Okay, so what are the new bases? So see, U and V are basis open, right? So again there is some B1 belongs to tau x, and B, or rather you can say not only tau x, you can say that Bx, right? What were my symbols? Bx, yeah. So you can have an element of the basis itself, and B2 belongs to By, because see, U is open in X, so you can have a Bx, right? Such that your X is the element of B1, which is inside U, and Y is the element of B2, which is inside V. Okay, so this is the definition of the topologies, and U and V are open sets in respect to topologies, right? Now what is the corresponding product of these two, B1, B2? So now you check that your X and Y, this is the element of B1 cross B2, and which is obviously inside U cross V, and it is also obviously inside W. So what does that mean? That means W contains one elements from the from that set, and that means this implies that this B is a basis for the product topology, right? We just proved that every open sets in product topology you can have at any points, obviously you can have an element of the basis, right? So this is basis for product topology. Product topology on X cross Y, right? So though you can define the product topology from kind of Cartesian product of all open sets as basis, you can have a smaller corrections. What is that? That is the Cartesian product of all basis element of the individual topology. That is also forms a basis. Okay, clear? So now obviously you can have you can ask for examples. So and the standard example obviously comes from real numbers. So obviously you know the Euclidean topology, so you can define Euclidean topology on the higher dimensional space also. So let me start with 2 dimension. So Euclidean topology, or the standard topology, whatever, on R2. What is that? So this is R cross R. So you can think X and Y both are, right? And you know there is Euclidean topology in R, and Euclidean topology in R, and then you take that, right? So what is the basis element? So basis element will be of the form some A1 B1 cross A2 B2, okay, where these A1 A2 are in the first component, and B1 B2 second component of, right? Okay, first component of R, second component of so this will form, say, basis element. So what does that mean then? So these are nothing but the open rectangles. So open intervals become the open rectangles there. So you understand? And we already proved in last class that these open rectangles and open circles, in the interior open circles, they also form the same topology, right? So you can choose this is one of the basis element, obviously. Okay, so and this is nothing but the product topology, which is actually the equivalent topology, which is actually nothing but the product topology on R, both, right? Okay, now now question is that do you have So this is one way of defining topology from basis. But in our last lecture, we learned something called sub-basis, right? The question is that can you define these topologies in terms of sub-basis? And the answer is yes. So you can do similar thing with something called sub-base, and we will have the same topology for this finite number of cases, like two product, three product. Okay, I will come to the case where you have like infinite product, and then obviously these two are not same. Okay, so now before that, let us define something. So let me define something called projection maps. Okay, so so let me define the projection map pi1 on the first coordinate. Okay, so we have this, and then you define x. Okay, so what is this? So this is the map which takes this kind of tuples to x. Okay, and you have another obviously naturally you can define the map x cross y to y. Okay, such that pi2 of xy map to y, right? Map to y, and this is called projection of this. So pi1 and pi2 are called projection on first and second components or factor, whatever components respectively. Okay, so projection of first component, projection of second component, and obviously you can ask the natural question from here that is they have satisfying nice properties, like so if you have a element of that topology, and if you apply the projection maps, what about that elements? Or if we pull back the projection map, what will be the open elements, right? So let me just define such things. So let me start with that. So if suppose you have a u which is inside tau x, that is open in x, then what about this, the inverse or rather fibers of u? So this phi inverse of u. So what is this? So this is what? This is called the fiber of u, right? So what is the fiber of u look like? So can any guess? So you say it is open inside x, and you want to know the pre-image of u inside x cross y, and now you check that this is nothing but is u cross y. Okay, what does that mean? That means okay, so in pictorially, so u here is u inside x, and this is projection is u cross y, so this is nothing but this. Can you understand that every element here on interior of this kind of infinite cylinder or infinite rectangles, they map to this small interval, right? This is obvious, right? Can you see that in the pictures? Because every element inside these infinite rectangles, the x coordinate is inside these small intervals, and hence the projection is this, right? And this infinite small interval, infinite rectangle is nothing but u cross y, right? Similarly, you can check that for any v which is open inside y, the fiber of the fiber of v is this with respect to this pi2. Okay, pi2 inverse of v, which is nothing but, and there is no price for guess because it's as simple as that, x cross v, right? And pictorially this means that you have something here, and you have the infinite, this rectangles, and if you take projections of any things whose y coordinate is inside V, so they will map to this. Okay, they will map to this. Okay, so this is the nice property. What is the nice property? That these projections preserve the property that whenever you are taking pullback or pre-image of open set, it becomes open, right? Because see, this is also open in the tau, which is nothing but tau x cross tau y, the product topology. Similarly, the other one also, see, this is also open inside tau, this is u cross y, right? Because u is open in x, y is open in y, right? So what does that mean? That means that these projections are having this property, they are pullbacking open set to open sets, and these kind of maps has a nice name we will define later. This kind, they are called continuous maps. Okay, this property is satisfied, but I will define later. First, let us try to understand that what is the advantage of this property. The advantage of this property is that the moment you know that what is, suppose you know this u and v, and then if you want to find out what is the intersection. Okay, now if you want to find out what is the intersections, so that is obvious, the intersection of these two sets. Okay, so now you check that clearly. Thus this pi 1, these fibers of u and the intersection of fibers of v, right? So this is obviously u cross v, right? And that is again, so let me draw pictorially. So one way you have the infinite things, another way you have these infinite things, and this is your u, this is your v, so this is your u, this is your v. Okay, and if you take u intersection v, this is this one, and that is nothing but the intersection of these two things, right? Okay, so so this is the nice property that is going to help us to define kind of topology generated by the subbase. Okay, now let us prove this theorem. Okay, so now we are in a position of proving the theorem. Okay, so so the collection. So there are two such things. So one is the fibers of under the projection pi 1, such that u belongs to tau x, and union with another fibers which is with respect to the projection pi 2 of v, such that v belongs to tau of y, right? So this collection is a subbase for a subbase, or okay, whatever subbase for the product topology. So what does that mean? That means product topology on x cross y. So this means that the product topology also can be generated by this subbase. Okay, so we just saw that product topology can be generated. We define it in one way, and then we saw that this is actually nothing but the generated by the basis which coming from the corresponding product of corresponding basis element, right? Now this is another way of defining the product topology. Okay, so what does that mean? That means that if I generate the topologies from this set S, the topology the topology generated by this set S is exactly the product topology. Okay, now how do you prove this thing? So so we have obviously proof. So let this tau be the product topology, topology on x cross y, and let me write it tau1 equal to the topology generated by the subbase, okay, on x cross y. So I have another topology, so I know how to generate the topology from subbase, right? Obviously first you need to prove this is subbase, but this is obvious. Okay, I will give you a proof why it is subbase. So obviously subbase means that should covers the full space x cross y, right? And this covers full space, because if you take these fibers of, okay, so I will come to the proof. Okay, before that let me just finish this thing. So this topology is topology generated by the subbase. What does that mean? That means the elements of these are coming from the union of the finite intersections of the element of S, right? Or rather than the basis element of tau1 is nothing but the finite intersection of the element of S, right? Okay, so on Y, then the theorem is that tau and tau1 are same. So the product topology is same as the topology generated by the subbase here. Now, so first let us so okay, so then we need to prove this. Then this, okay, so I should not say then here. Then we will show that tau and tau1 are same. Okay, now let us first check that this S is a subbase. Okay, how to check S is subbase? So what does that mean? So if we take any such collections, so that will obviously they should forms this, right? So how to check? So x cross y, this should be a cover. So can we write down x cross y union of this thing? And the obvious, because now you choose, because okay, so so this is, you can write down as union of that say pi 1 inverse of u, okay, and then u belongs to tau. If you choose these things, now you see that this is exactly this, right? Because so each of those things is nothing but what? This is nothing but union of element of the form u cross y, right? And then you are varying over u, right? So if you vary over all those u's, then you will get x, right? This is a topology, right? So x it's inside that. So this is obviously this is subbase. It belongs to, okay. So this S is a subbase. This is the proof is trivial. Okay. Now how do you check that these two topologies are same? The topology coming from the basis element, which is the product of the individual basis element, and topology coming from the subbase, which is the union of the finite intersections of S, right? Yeah, so this is now to prove something. Then you have, see, there are two topologies, you know. Now one is obvious, so you check that this tau1 is inside tau trivially, right? Trivial. This part is trivial. Why? As as this S is the open set, right? So S is element of tau. Okay, S is element of tau because S is product of open sets, so they are element of tau. Okay, and hence if you take anything, this implies this tau1, which is generated by S, that has to be also inside tau. Okay, so tau1 is a topology generated by S, and that has to be tau, because tau is the topology which is closed under finite intersections and arbitrary unions. So hence tau1 is subset of tau. This one is obvious. So now conversely, or rather you can say that otherwise. So if I have to prove that tau is subset of tau 1, it is enough to prove that the basis element of tau is inside tau 1, right? Now if you choose, so let us say u cross v belongs to tau. Okay, so what does that mean? That means u is open inside tau x, v is open inside tau y, right? So this is open inside tau, and then we know that u intersection v is nothing but intersection of pi 1 of u into pi 2. Okay, pi 2 inverse of v, right? So the fibers of u and fibers of v, if you take intersection, they will nothing but u comma v, right? So what does that mean? That means every element of the topology tau can be written as the finite intersection. See, intersection of two elements only. Finite intersection of elements of S, right? So this implies that u comma v belongs to the topology generated by S, which is nothing but tau 1, and hence tau is a subset of tau 1, and thus both are equal. Okay, so this is the proof actually. So this shows that if we have if you define the sub base in terms of fibers of open sets in the individual topologies, then they also form a same topology. I mean, the sub base also generate the same topology. Okay. Now question is that is these things true for kind of arbitrary space? Okay, the answer is no. Okay, so for example, you can do this process till finitely many things, right? So if you do finitely many of like finite times the same process, product of finite number of things, then you will have okay, so you'll have okay, so for example, instead of two things, instead of two things, suppose if you have finitely many x1, x2, some xn, then also you will have the same topology. Then also this the topology generated by the basis and topology generated by the sub basis, okay, they will form the same topology, and that is nothing but the product topology. Okay, but if we have infinite connection, then what happens? Okay, so for infinite collection, this is not the same. So what does that mean? So suppose now let me define my set X as this infinite collection product x1, x2, and some infinite collections. Okay, maybe I will write down these as these symbols. This product of x alpha belongs to lambda. So I don't know what kind of lambda is this. It can be arbitrary. Okay, any arbitrary. Okay, so this alpha is some kind of index set, and then you are defining this kind of Cartesian product, and the elements are what? So elements are kind of x alpha. You can write down this is elements of this alpha belongs to lambda. This is elements of this product of x alpha belongs to lambda. Okay, so this is kind of coordinates. You can think this kind of sequence kind of thing. Okay, it has a name, it's called net, but let us assume that this kind of sequence of kind of thing, right? So okay, so this is you understood. So this is, I will call this is a product of or Cartesian product of topologies. Okay, and for individual x, suppose you have topologies tau x alpha, this is topology on x alpha, or maybe tau alpha, whatever you prefer. You can write down tau alpha, no problem. Okay, now with the help of our previous idea, so we can define two topologies. One is coming from the basis, So what does that mean? That means so maybe I can write down the theorem form. Okay, so suppose you have this x alpha and tau alpha topology such that the tau alphas are generated by the basis say b alpha. Okay, suppose then if you take the collections of the forms which is product of all such b alphas, so my b is nothing but collection of the set like all the product of these elements of say b alpha belongs to lambda, such that this b alpha is element of the script b alpha, the open what is that the basis of the alphath topology. Okay, then this collection also forms a topology basis. This collection also forms a basis. Okay, similarly what we prove for 2, it is true for any arbitrary collections. Okay, any arbitrary collection of collection product, they will form this, right? Okay, so so what is this topology? First of all, if you do these kind of collections, and the answer is that this topology is this is one topology, and we will call this topology as something called box topology. Okay, so before that, let me define another way. So another way is what? Another way is using the idea of subbase. So what is that? So you have projection maps, right? You have this some alpha projection map that from products of that x, which is product of x alpha not to lambda to that alpha coordinate. Okay, so only everything mapped to the alpha coordinate, right? So if it is the alpha projection, so and obviously open sets, pull back open sets to open set. Now I can define obviously this x alpha of some sets, right? Now let me write down u, where u, so this is my collections, so u is inside this tau alpha. Okay, and this is, let me write down by s alpha. Okay, so this is kind of fibers with respect to the alpha projections, right? Now if you take all such alpha projection, beta projection, every such elements, then what will be happening? This union will forms a subbase, right? So how do I define this thing? So I will define that okay, so let me define by this S is nothing but my union of all such sub alphas. So S is nothing but union of all those is alphas, such that alpha belongs to lambda. Okay, so what does that mean? That means for each coordinate you have these kind of fibers, and then you are taking the union of those fibers. For example, here I have, see, for finite case, let me show you again. Yeah, see, finite case, what was my S? My S was union of these two things, right? Yeah, so this union, this first one is kind of, you can say S1, this is S2. This you can write down, first one you can write down as S1, this is S2, right? And then you're taking union. Now instead of finite number of things, if you have infinite collections, arbitrary collections, then you can define by this union of this alpha. So obviously, clearly, this S forms a subbase, and you can define the topology. So this is a topology generated by, say, maybe write down tau, which is generated by S. Okay, and there is another topology, say maybe celebrated tau dash, that is generated by the basis element, right, which I just defined before, this basis element. Okay, the question is that are these topologies are same? We prove that for finite cases this is same, right? We prove it for true, but it is true for finite case also. The answer is no. These two are not same. Okay, so these two are not same, and it has a name. So this tau represented by the subbase, we call this a product topology. This is the actually product topology. Product topology on these collections, this collection product of X alphas, and this topology which is generated by the basis is called the box topology. Box topology. Now what is the general difference that we should understand? In the box topology, you see open sets are nothing but the Cartesian product of original open sets. Okay, and so there might be infinite such open sets which are not the full sets inside box topology. But inside product topology, what happened? Now product topology, the basis elements are what? This is nothing but the finite intersection, right? Remember, this is subbase. This X becomes the subbase. So what does that mean? That means the topologies are nothing but the union of the finite intersections of element of S, right? So what does that mean? Finite intersection means, that means in this topology, the product topology which is generated by S, the basis element will be of the form like this. They will be something, some finite intersection of the elements. Maybe let me write down alpha 1 or something, some u alpha 1 intersection alpha 2 of u alpha 2, some some alpha k of u alpha k. Okay, so this will be the basis element, right? So what does that mean? So that means the rest. So if you want to write down as a coordinate, then what will be the coordinates? So for these alpha 1, alpha 2, alpha k position, you are getting from the original, the points are coming from u alpha 1, u alpha 2, u alpha k, and rest positions are nothing but the full set. So what does that mean? That means you can write down your B as intersections of this u alpha, okay, because this intersection is nothing but the Cartesian product, right? So you can write down the Cartesian product of u alpha. And the interesting part is that this is only for finitely many alphas, like alpha 1, alpha 2, alpha case. This is fibers of that set. Other than that, everything is full set. Okay, so where you can write down where these u alphas are X alphas, the full entire space, except for this final limitation, except for alpha not equal to alpha 1, alpha 2, and alpha k. This position, it is nothing but pi 1 u1, right? Okay, so other than that, the rest are the full space. But in the box topology, this is not true. The box topologies, all the positions may not be even the full space. It can be any proper subspace of the full space, right? So what does that mean? That means, so thus you can easily say that the box topology is finer. So there are more open sets in box topology than product topology, right? So thus the box topology is finer than product topology for infinite or arbitrary infinite Cartesian product. Okay, Cartesian product. Okay, and for finite Cartesian product, they are same. This is obvious, right? When you take the finite Cartesian products, and for the finite Cartesian product, the box topology and product topology are same. Okay, because the tuple generated by the basis B and the sub basis S are same. Okay. Okay, so I will stop my lecture today here. Okay, and we will discuss some more interesting results in our next class. Okay.